Now let's talk about acid catalyzed hydration. When you go to the pump and you fill up your gas, you might see a tank or a pump that says contains up to 10% ethanol. And you might be thinking, wow, there's a lot of farmers out there making ethanol or biofuel for this process. Very little of that is being used to produce ethanol. Most of the ethanol is produced by petroleum. So during the extraction of natural gas and things like that, ethylene might be produced. There's also ways to make it. And this is basically treated with water and special catalysts, pressures, and conditions to give you ethyl alcohol. So ethyl alcohol, well, let me draw it like this. Ethyl alcohol is the hydrated ethylene, okay? We are basically adding water across those two carbons of the alkene, okay? So the vast majority of the ethyl alcohol that you get in your gas tank, or that it's in your gas tank right now, was produced by this method. Now, we don't form primary carbocations, and we're not going to discuss these special catalysts. We're going to talk about more stable carbocations and more traditional hydration reactions, okay? Now, when you treat an alkene with water, you need for there to be an acid catalyst. And the acid catalyst is on the bottom of this arrow, okay? So here's your stoichiometric reagent, okay? You might have 2 or 3 or 4 moles of that. It's in excess. And down here, it's in catalytic amounts, okay? It could say cat, or it could say cat with parentheses, or H plus cat, something like that, okay? So we're not referring to pets, we're referring to a catalyst. The chemical reaction here follows Markovnikov's rule, and you get an alcohol, a more substituted alcohol, okay? So the alkene is the starting functional group, and the alcohol is the final functional group, and it's kind of like the reverse of an elimination reaction, right? So this is called hydration. It's as though the alkene is drinking water. I'll draw the H in there, and here's the H2O that you're adding, okay? The mechanism is going to involve formation of carbocations. And in the first step, you involve your catalyst, okay? So we attack H+. Now, the H+ could be sulfuric acid, toluene sulfonic acid, phosphoric acid, many different things. But I just draw H+ to keep the mechanism easy. And this is P for protonation, okay? And again, you want to stick the hydrogen on the richer so that you have a more substituted carbocation on the other. So here's a carbocation. And what happens is water is going to engage this. Water is a nucleophile because it has lone pairs on the oxygen atom. And the oxygen is going to attack that carbocation. Okay, so that's A for attack. Now, what you get from this process is your protonated alcohol. Okay. So you have an H here, and you have an H here because H2O is 2 of them, right? Now, here's where water is going to deprotonate. So you have water that's in large excess being used for this chemical reaction. So this acts as a base, and it's going to remove that proton from your molecule, and we call that process deprotonation. And so this is PAD for short. So that's the PAD mechanism, okay? And it works for pretty much all the different kind of alkenes we see, especially if you form secondary or tertiary carbocations. And water in the presence of acid will do this reaction, okay? There's a couple points I want to point out here. It follows Markovnikov's rule. Okay, so we say that it's regioselective. The rich get richer. You form more substituted alcohols. And the other thing is the stereochemistry. it's not stereoselective. So you form both enantiomers. Now, I specifically picked an example that was achiral, so we wouldn't have to talk about too much at the beginning. But that's when possible, okay? And so we call that not stereoselective, all right? So that's pretty much it. Let's go ahead and do some examples here, draw the products, and then we'll draw stereochemistry after that. All right. So problem 9.11 says, indicate whether you would use dilute sulfuric acid or concentrated sulfuric acid to achieve each of the following transformations. In each case, explain your choice. I'm kind of skipping that. I don't care if you know the concentration of that, okay? Now for question 912, it says draw the mechanism for each of the following transformations. You have to use the given molecules that they give you. You can't invent something of your own, okay? So if they're drawing H3O plus, you need to draw it out. And we're drawing a product here, okay? We can't draw something else. We have to draw that product. So let's go ahead and engage this acid, okay? So that's basically H plus, but since they gave me H3O plus, I need to draw that, okay? So in the protonation step, we get this nice stable carbocation, and then we have water present. All right, and then in yellow, I'll draw my curved arrow. That attacks. A for attack. You form the protonated alcohol. Be sure that you draw the plus on the oxygen. And then what we have is water that's deprotonating. D for deprotonation, okay? Now, when this step forms, you form H3O plus, and you remake this catalytic molecule, okay? So after this happens, you're going to form H3O plus, and that goes on to catalyze more of the chemical reaction. As long as there's water in there, it'll keep doing it and doing it and doing it until it's all consumed. Molecule B, we have dilute sulfuric acid, it says. Now, dilute sulfuric acid is the same thing as saying you have bunches and bunches of water and a bit of acid, okay? The product they're showing here is tert-butyl alcohol, okay? And so what I'm going to do is use these combinations. So first step, we have protonation. You form a more substituted carbocation. Water is now going to act as a nucleophile and attack the electrophile. Okay. And then you're going to have water that comes in and deprotonates the molecule. Okay, so that's pad once again, and this is problem 912b. 912c, similarly, you have an alkene, you have water, and Klein uses brackets around H+. That's the same thing as saying H+ catalytic in other textbooks, for example. And what you form from this is 1-methylcyclohexanol. Don't worry about naming alcohols yet unless your class has talked about it. All right, so what do? We attack H+. We don't really say attack H+, we say protonate the molecule. When this occurs, we form a very stable or a more stable tertiary carbocation. And so the next step now, once again, you can see how this is a lot of repeat, but you've got to do it to get that muscle memory. And remember these reactions. So that's A for attack, and you form the protonated alcohol there as an intermediate. And then we have some water present. Some students write OH2 like that. It's a little bit sloppy, but you can do that. And deprotonate your alcohol to give you your neutral alcohol, okay? So those are practice drawing mechanisms, okay? And that's the end for this beginning part. We've talked about sections 9.1 through 9.4 in the Klein Organic Chemistry 2nd edition textbook.